tau 2n minus 1 b to n of 1/2 2n factorial, and the second the derivative, the 2nth derivative of Li2 e to the minus z tau, oh, I put that here already, tau to the 2n minus 1. Okay, this forever means that.
It's not worth, it's again asymptotic. By tau, it's not, because it's divergent sum.
Yeah, this is just a formal power series.
It's form power series.
Yeah. In tau, with coefficients that depend on z. Okay, so that is a lemma, and what we will do is we will consider the Borel transform. The Borel transform, let me remind you, there is a confusion actually about Borel and Laplace, and I'm going to use the correct kind of usually what I call Borel, I think, is what you call Laplace. So let me define it for you. So the Borel transform, no, I mean a Laplace integral is a Laplace, I mean cannot be. So the Borel transform of tau to the n plus 1 is xi to the n over n factorial. Here n is greater than or equal to 0. So it takes positive powers of tau, it replaces them by another variable divided by n factorial. Sorry about this xi, but this is xi actually. No, xi. Okay, so it's Greek letter xi, yes. Yes. That's definition of what Borel transform is.
It's a definition of xi.
Oh, okay.
That's how Greek people write.
Right, xi. Yeah. That's a definition, right? Yep.
In Lemma, under the assumption that f tau of z goes to
Yeah.
Some people could say it's
Yeah.
number 7, but
That's okay. Yeah, I agree. It looks a lot like number 7.
it was before.
It was before. So our theorem is the following, that okay, so let's define the Borel transform of this power series to be, it's a power series that depends on a variable xi and it depends on z, so that's the Borel transform of this phi hat. And the theorem is a formula for this function. And the formula is the following. So there are some analytic assumptions. So z is a complex number of absolute value of imaginary part less than pi. And xi is a complex number so that it is less than pi minus the imaginary part absolute value. Then, under these assumptions, we have a formula, an explicit formula for the Laplace, for the Borel transform, which is 1 over 2 pi I, sum from 1 to infinity, minus 1 to the n over n square, and then 1 over 1 plus e to the xi over n minus z, plus 1 over 1 plus e to the minus xi over n minus z. Okay, that's a formula. A formula for what? So in particular, this formula, so the right hand side is well absolutely convergent as a function of xi. Around 0, absolutely convergent at xi equals 0, with radius of convergence exactly pi minus imaginary part of z. Okay, so this series was factorially divergent not because of this. This is only exponentially growing, but this term here, because it takes a 2n derivative, A 2n derivative brings a 2n factorial, so this is factorial divergence series. So after you divide by the appropriate n factorial, you get a germ of an analytic function around psi equals 0, but it is not just a germ, this is a global formula that allows you to prove in particular that this is a meromorphic function of psi in Borel plane. And not only that, you get much more. You get bounds, and you also get the location of the singularities, which are moving and depending on z. Okay, so in particular, so it follows that this function here has simple poles at psi equals n psi m when n is a non-zero integer and m is an integer and psi m is z plus 2m plus 1 pi I. So these are the simple poles with residues. Cn, it only depends on n but not on m, and the residue is minus 1 to the n over 2 pi I n. Okay. And there are a few more things that follow. So I guess let me just put all the analysis here. Also, it follows, so some bounds follow, for instance, that when 0 is less than delta, less than pi minus the imaginary part, then g psi z in absolute value is less than or equal to the maximum of 2 and the pi square over 3 sine of imaginary part.
So this should lie in this strip here.
Yeah, that's right. And psi is in this strip, which is delta apart from 0. So these are all the psi's in C whose distance from R plus is less than delta.
But your number z also should be have imaginary part less than pi, I suppose, otherwise.
Yes, that's right. Follows from here. Okay. All right, and so that is that's the structure in Borel plane. It is not very common that after you do the Borel transform, you get a germ that has a global formula, and even less a formula that it is meromorphic, but that is the case in our example. And it also follows that, so also follows, no, now we need to talk about Laplace transform. So let's talk about Laplace transform. Definition, Laplace transform. So, the Laplace transform, of a function f of tau is the integral of e to the minus psi over c over tau f of c dxc if f is, let's say, in L1, for instance. That's the Laplace. Okay. So our first theorem was a global formula for Borel transform. The second theorem is a formula for the Laplace integral. So the formula says that if we took the Laplace integral here, and now it's a function of tau, and we add to it what we took out, namely the exponentially large correction, then this, which is an abstract Laplace integral, is nothing but the logarithm of Faddeev's quantum Dialog function. This is Faddeev quantum Dialog, and I will tell you what it is. Okay? In other words, you can look at this first order Q difference equation, and you can look at the formal power series solution. It has a global formula, and if you actually do the Laplace just on the positive reals, you are getting, among all possible solutions to this linear Q difference equation, I mean, you are getting exactly Faddeev's quantum Dialog.
Then you put it in from the beginning, because I guess it's not true, this lemma for all solutions to this.
It's kind of formal things if you substitute.
Excuse me? This is a formal power series.
Yes,
it's not
but there are many solutions to the equation above.
It's the same
Yes.
power series.
Yes, all solutions to this equation have the one and only formal power series solution.
What about 5 times this function?
Yeah, you should not.
No, normalize this leading term.
I did normalize it.
Yeah, you have to
I
see what
did
is
normalize.
it at infinity.
Yeah, but I did normalize it from here.
It should be
that's
something
the
plus.
Yeah.
Okay, substitute the things to formal. Yeah, okay.
Yeah. So, okay, so Rinat was actually bothering me for a reason, but okay, so the limit of f tau of z as z goes to minus infinity is 1. But just because you normalize it by this, it will not necessarily make it unique in any sense. And as a corollary of this story is that in particular the Laplace transform, so the Laplace transform satisfies an additional Q difference equation, namely this one, minus pi I is equal to 1 plus e to the z over tau f tau of z plus pi I. Okay, so there are doubly periodic functions out there, I know, there are all kinds of things, but the fact is that you uniquely reproduce Faddeev's quantum Dialog. So let me say a little bit about what is Faddeev's no, maybe I'll tell you about some easy things first of all. So first, how do you prove this lemma? Okay, so let me say something about proofs, and then I'll draw a picture. So the proof of the lemma.
There's no tau in the argument of that tau here.
No.
There's
It's
tau.
a different equation.
Oh, okay.
Tau, no tau. Okay.
Oh, yeah. Well, b square is tau. But I didn't tell you what is Faddeev's quantum Dialog. Okay, the proof of the lemma. Proof of the lemma. Okay, so that's not very hard because, well, we take the logarithm, right? So we have the logarithm here, logarithm of f tau of z plus pi I minus f tau of z minus pi I is minus the logarithm of 1 plus e to the z, which is the derivative of Li2 of minus e to the z. And then this thing is an infinite order differential operator because it is shifts. Is there a tau? Sorry, pi I tau. Thank you, pi I tau. Absolutely. And then this becomes now 2 hyperbolic sine of pi I tau applied to the log. Okay, and now you divide this by that, and you use that x over sine h is the sum of the even Bernoullis 2z to the 2n over 2n factorial, and it goes z is x, and it goes from 0 to infinity.
Okay, so something called Euler numbers.
Yeah, actually these are exactly Euler numbers. And the odd ones are 0, just like the Bernoulli. The odd Bernoullis are 0, except B1, but this one is also 0. Okay, so that is just the proof of the lemma. So now let me tell you about the proof of this formula here, because you may wonder, how would you prove this, right? Just one thing to say, I mean, assuming that we can prove it because this formula is explicit, and we know the zeros of exponential of something plus 1, so it's the zeros of this function that gives you the poles here, and these are simple, and you know this formula implies that, and it will also imply this as well. Okay, but how do you get an explicit formula here? So let me okay, so this proof of this, well, of this one, of theorem 1, uses a proposition that says if we consider the following series tau z which is a sum from 1 to infinity b to n a half 2n factorial second 2 pi I tau to the 2n minus 1. So if we consider this, then and gf of xi the Borel transform, then the formula for the Borel transform is the same up to the sign here, actually I over 2 pi, 1 to infinity minus 1 to the n square, and here the second partial of z plus xi over n plus the second partial of z minus xi over n. Okay, so if we prove this, then that follows by using the specific f, namely the one that appears here. Okay, so let's prove the proposition. So how do we do this? We need to recall what is Hadamard product. Recall the Hadamard product.
H Hadamard.
Hadamard.
Ah,
Hadamard?
Hadamard, yeah.
So it's the poor man's product, right? Okay, so now let's start. What is this? So we have a sum. I take this formula here, 2n a half, 2n factorial. I take this power. I take 2 pi I to the 2n minus 1. I go from 1 to infinity. And I'm going to replace tau to the 2n minus 1 by c to the 2n minus 2, but I divide by 2n minus 2 factorial. That's the formula. Now what I like is to separate the Bernoulli from the rest. And I can I just do. Two pi I to n minus 1, c to n minus 2, to n minus 2 factorial. Okay? It's actually elementary. So now I can sum both. This one I will skip the kind of intermediate steps here, so let's call this thing f1 of c, and let's call this thing f2 of c, but it depends on z as well. So f1 is basically the generating series, but you have to kind of renormalize it a little bit. So it is e to the c half minus it. It has to be massaged a little bit. So because the 2n minus 2, I need to take somehow two derivatives or two antiderivatives, and this is regular, that's why I need to remove that. I mean, this is just a little generating series. And f2 is equally good. It wants to be, and in fact it is, with the pi's and the i's, it is the second derivative plus the second derivative of z minus 2 pi I c. Why? Because we're doing even derivatives, and we just use Taylor series. If you think about it for a moment. Okay, so this is Hadamard product, but we are almost there, but we need to convert this into a formula, and the conversion is by writing the Hadamard product. Hadamard. Yes, Hadamard product. So we write it as an integral near 0 of f1 of s, f2 of c over s z ds over s. A contour, near 0, right? Okay, and analytically we're all good, because this series is O of 1 over s cubed, and this is O of s, so convergence is fine. And now we increase the contour and we collect residues. And all the residues are coming from here because of here, so the residues are at 2 pi I times, so here when that is 0, so we get residues at 2 pi I m. M is an integer, and you collect. So the residue, all you need to know is that the residue at 2 pi I m of f1 is actually minus 1 to the m over 2 pi I m. So this m here with this s evaluated at 2 pi I m gives you the n squared term. The n squared term here. And then this is regular at these residues, so it evaluates the 2 pi I cancels with this, and you have xi over m. Now my m became n. I actually fold it twice because instead of summing over integers, because it's even, I sum over the positive ones, and here's the answer. Okay? It's really elementary. Just elementary manipulations. Now, okay, let me actually plot, because I do want to plot the emerging picture. I wanted to say that there is a picture that emerges here. So the picture is the following. We have here is xi0, here is xi minus 1, xm is z plus 2m plus 1 pi I. So these are 2 pi I apart. And then there is one here, and then there is one here, and one here, and one here. And they also come with the negatives. And then in these rays, they have to be multiplied by n. So this is xi0, this is twice xi0, this is 3 times xi0, and so on. And then on the other ray, you also multiply by 2 and by 3. And on the third ray, you multiply, that's going over the line. So basically we have all these rays.
Actually, the picture is not so good because you wrote things not really negative on the left. No, these points which you draw on the left, the vertical axis, are not negative of points which you write on the left.
Oh yes, that's right. They're not. Yeah, that's right. I agree.
Like
It's a shift. Yes. So this is some star-shaped picture that shows the kind of singularities, where the singularities of this function are. Okay. And what we are doing here is we are taking, so these are two vertical lines here, and then they are scaled by a factor of 2, 3, and then these are the other lines somehow with a factor 2, 3, and we're taking the Laplace integral along here. We're doing the Laplace along the angle 0 in the positive reals. That's the one that's going to be Faddeev's quantum dialogue. Of course, our function is meromorphic, so we don't have any issues about multivaluedness anywhere. And we can take its Laplace anywhere we wish. We can take the Laplace along any ray. So this is the ray we choose. Of course, you can choose any other ray here. And if you choose that ray, you can call the answer Fm, where you're doing a Laplace integral, the integral e to the I theta m of z infinity e to the minus c over tau g of xc z dxc. This is any other Laplace integral between consecutive rays. So there are infinitely many rays, and one of them is this one. This is also special. And there's another one here. So there are three interesting rays. So this is the pi I direction. This is the minus pi I direction, and they're all the intermediate ones. And I gave you a formula for the answer here. Let me actually tell you an even easier formula for the answer here. So the difference between a Laplace transform here and a Laplace transform there is the result of collecting residues along the way. So in fact, I will give you a formula. So I'll give a formula for two consecutive ones. It depends on z, of course. Okay, we will give such a formula. And what will this formula be? First, let me draw the picture. So if you want the formula between one Laplace and another, that's the same as this Hankel contour. Singularities are simple poles, so therefore you just apply the residue theorem to the original function. So this is apply residue theorem to the function that you're integrating at the appropriate residues. Now, they are not one, but they are infinitely many. And what are the residues? Let me tell you what the residues are. I did realize at 2 a.m. last night that my real part should be negative. So the formula I'm going to write down is a little off. Okay. So this is a sum, n greater equal to 1. I have 2 pi I have Cn, I have e to the minus Cm of z n over tau, where this is the sum. My Cn was here, but I think it got removed. It's the minus 1 to the n over n. My Cm also got removed. It's z plus 2 pi I m, 2m plus 1 pi I n tau. And I'm summing, so this becomes manifestly a logarithm of what? Of 1 plus e to the minus z over tau q tilde 2m plus 1, where q is e to the 2 pi I tau and q tilde is e to the minus 2 pi I over tau. And as I told you, my real part should have been positive, so in fact this sign should be a plus sign. Okay, so in the formula that I will match it with Faddeev's quantum dialogue, this should be a plus. This is actually because, I was secretly working on this other if the real part is negative, I should be working with these and not with these. Anyway, I'm not going to fix it right now. So these are sort of instantons. This is the mth instanton correction. So you have infinitely many rays. Every time you jump in a ray, you pick up an instanton correction. So the formula here minus the formula there should be the sum of all instantons. And what will the sum of all instantons be? well, if my signs were correct,
So here you assume that tau is complex, right?
yeah. Yes, here tau is complex. That's right. So, okay, so we will collect the instantons for a moment. So let me make the connection with Faddeev's quantum dialogue, and I still owe you the proof that the Laplace here is Faddeev's quantum dialogue. But I cannot give you that proof before I tell you something about Faddeev's quantum dialogue. Now I don't need this anymore. Okay. So Faddeev's quantum dialogue. So at least in one version of it, maybe the one that is not it is the ratio of two infinite Pochhammer symbols. The tau is going to be b squared, and CB is I half b plus b inverse. And if you actually change variables as I was before, you can find out that this is what I called f sub tau. This is a little cleaner, q to the 1/2 e to the z q infinity minus q tilde to the 1/2 e to the z over tau q tilde infinity. And you can see that z minus pi I tau over z plus pi I tau. So if you shift z by pi I tau, the denominator is common. So here denominator does not change. By this shift, because it's a z over tau. But numerator changes, and in fact what you find out is that it becomes 1 plus e to the z, because the new numerator picks up a higher power here. Okay, so this is one of the versions that you can see of Faddeev's quantum dialogue function, that it satisfies the equation that we had. But we will need the integral version of it. So integral version is we will need the integral version. Exponential e to the minus 2i x z dx over x and notice we want to after all, what we want to do is we want this, which is essentially, up to a change of variables, the integral here. Now what is this integral? This integral is basically the integral of 1 over hyperbolic sines. And we're going to use a formula due to Voronovich. So Voronovich, if I'm not, Voronovich gave a introduce the following function: log of 1 plus e to the theta xi divided by 1 plus e to the xi minus z dxi. Here theta is positive, imaginary of z less than pi. So he introduced this function here, which does not look like a Laplace and does not look like the logarithm of EB, but the proposition is that if you take Voronovich at 1 over tau at z, you get minus 2 pi I log of phi b of z over 2z 2 pi b when b squared is tau. Okay, and here tau is, let's say, positive. Okay, so this is one proposition that was implicit in Voronovich's work, and another proposition is that our Laplace transform is going to match Voronovich. The Laplace transform is going to match Voronovich. How exactly? Minus 2 pi I Laplace as a function of tau is minus the divergent term Voronovich 1 over tau z. Okay, so we need to prove this and we need to prove that. And if we do that, then at least we have identified the Laplace transform along the positive real axis with Faddeev's quantum dialogue. Okay, so how do you prove 1? Okay. So if you look at this and you look at this, what do they have in common? They are sort of the integral, what do they have in common? There are two functions here. One is log and one is 1 over 1 plus e to the xi minus z. And they are paired. And there are two hyperbolic signs here. So the proof of this proposition uses a special function identity, which is that the Fourier transform of 1 over cosh is 1 over cosh. Okay, so this is the inner product of two functions. The f is the log and the g, that g is not the same as the g I had before, is the 1 over. And then, I don't like this because this is going to be their Fourier. So this is the same as their Fourier. And you need to compute the Fourier of the log. But if you integrate by parts, the log will become 1 over 1 plus e to the xi. And after you symmetrize, is going to become the Fourier of 1 over cosh, which can be another cosh. And you turn the cosh into a sin. So that's the first Fourier. And the Fourier of the second is a similar story and will give you the other sin. So that's kind of the proof of this proposition 1. It doesn't just use complex analysis, it uses complex analysis coupled with the fact that Fourier transform is unitary. The proof of proposition 2 is a little easier, although we have to start with this formula and we need to match it with our explicit G. So let me tell you about the matching. Now, where am I going to write? I think I can do that here. Okay. So ready for the matching. So we need to do the integral. So what do we have here? W1 over t. W1 over t of z is the integral of log 1 plus e to the xc over tau 1 plus e to the xc minus z dxc from minus infinity to infinity. First of all, we're going to write it as the sum of 2. Second, we're going to change variables and make it the sum of 2, but of this kind. Now we folded it. E to the xc over tau 1 plus e to the xc minus z, and the other log of 1 plus e to the minus xc over tau 1 plus e to the minus xc minus z dxc. Okay, and now we're going to take out one term, which is the divergent one, and the remaining is just an integral, except that it now has a common factor, and then it has two more terms. And now we're going to write this as a sum of minus 1 to the n over n. And we're going to change variables because we want xc over tau, not xn over tau. And that's going to put the n over here. And it's going to pump the n to an n square. And we're done. Okay. How much time do I have? Okay, good. So the Borel resummation of our series produces Faddeev's quantum dialogue. Now what happens here? What happens here is actually a much easier story, a story that was in a paper of Marmi and Sozen. This is the story. So if you take the logarithm of Faddeev's quantum dialogue, which is this, and you remove all the instanton correction terms. Remember there was this minus sign, but I told you that it should have been a plus sign because my real part should have been negative. So if you remove from the log of this the sum of the logs of this, what remains is the log of this, e to the z q infinity. What remains? And what this is the Laplace integral. This is the Laplace integral in the pi over 2 direction. And this integral satisfies our equation because, in fact, this integral do I have it? I had it. is minus sum greater or equal to 1 of minus e to the z n q to the n half n of 1 minus q to the n. Okay, and this solves the difference equation, the q difference equation. But in fact, this solution to the q difference equation, it's even nicer. This solution is 2 pi I periodic with respect to z, right? Because manifestly there is the e to the z. And if you actually looked at the formula for the Borel transform that I gave you, the formula is manifestly 2 pi I periodic. And now comes the challenge. If the Borel function is 2 pi I periodic with respect to z, if I do Laplace, why don't I get a function which is 2 pi I periodic? Here it is, but here it isn't, because Faddeev's quantum dialogue is not 2 pi I periodic, it is quasi-periodic. And here it's neither periodic, nor quasi, So the reason is that this is a fact, and here we're integrating along pi over 2. These points, they don't just depend on m, they depend on z as well, because here's the z. They are moving points. So as these points move, and I shift z to z plus 2 pi I, they move vertically, but if I do my Laplace integral in the vertical direction, it is unchanged. On the other hand, if I do the vertical integral in the horizontal direction, and here are my z, if I move them with 2 pi I, I'm in another sector, so I'm in another branch, in another Stokes sector of my Laplace transform. That's why this one is not periodic, but this one is. So this is one solution, but then of course there is the other solution. This is the pi over 2, then there is the one at minus pi over 2, and it is actually basically the same story here. So this is when q is less than 1, but in fact the same formula works. Same works even when q is bigger than 1. In other words, the solution here, the Laplace transform, is also 2 pi I periodic. So here we have q and q tilde series. We peel off one by one the q tilde series, and we're left to q series, one defined here and the other defined there. But the important thing is that because we can move the Laplace transform from here to there, it follows that in fact our Laplace integral, which the Laplace integral on the positive real axis is well defined on the right half plane, but because you can collect the residues both forwards and backwards, you are able to extend it to the cut plane. So you have a function which a priori exists only on the right half plane, but in fact extends to a cut plane. Okay, and this picture is, I claim, general. So how general? So I'm gonna now remove all the formulas and focus on the aspects of this picture, and I'm gonna rotate it by pi I just because the complex Chern-Simons function is like that. So for the figure 8 knot, it has volume plus 4 pi square. There is a lattice like this. Keep in mind that this is about 40 and this is about 2. So the scale is much larger, and you can do a Borel transform. The interesting, Laplace transform. The interesting Laplace transform is here. So here is the site of the interesting Laplace. And then there are corrections, instanton corrections. until we go to the not so interesting, but still interesting part here at 0 now and pi. Okay, so here is where the state integral leaves. And here are where the functions that Don, Zagier, and I studied leave. They leave here for the figure 8 and there. And I will finish by telling you what is the state integral for the figure 8. It is a function of tau pi I x squared dx. It's absolutely convergent because there's exponential decay here at infinity in the cut plane. And this function of x can be written as 1 over root tau g of q big G of q tilde minus root tau little big, where G of q is a q series, n plus 1 over 2 quantum n factorial minus 1 to the n, and big G is the same one except that you multiply by a 6n plus 1. And you can peel off this series. This is the answer of the state integral here. You can peel them to get the answers here and there. This picture, however, has not been proven, but it has been experimentally tested, and we were able to compute numerically instanton corrections for up to about 10 orders of q tilde. So I'll stop. Yes, 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 absolutely, SL2C, yes. And whether there is some z-graded Hodge structure, you know, that explains this story, I don't know. Okay, I'm done.
Questions? I have this very stupid question. There is a simple story. You can see the logarithm of gamma function and have an expansion to infinity, and then we get Laplace transform, get singularities on the E2 pi iz. Yeah.
Yes,
and
yes.
This is kind of like Q version of this. You get kind of infinity many copies of this.
Yes, that's right. That's right. But for the gamma function, there is something we know about gamma that we don't know about Faddeev's quantum dialogue. So I gave you a formula for the log of Faddeev's quantum dialogue. But of course, so this is a Laplace integral. And if the log has a Laplace integral, then the original function has an exponential convolution of Laplace integrals. Exponential convolutions are generally impossible functions to deal with. I mean, you only know their singularities. Even the meromorphicity will break. However, for gamma, it is true that it is a Laplace integral of 2 branches of the Lambert function. And I don't know a similar formula for phi. However, I did ask Rinat, and he gave me a limit. There's a specific limit of Faddeev's quantum dialogue for which it becomes the gamma function. So, and the expansion of Faddeev's quantum dialogue involves Eisenstein series of odd weight, and therefore a formula that you have for the Laplace transform of gamma could hopefully be lifted to a formula for the Laplace of phi. I don't know such a formula, and I don't know it neither for Faddeev's, neither for itself. It would be very nice to know the answer here. If we know the answer here, we can prove actually rigorously resurgence of NUM series, which is which has been experimentally observed but not proven. Yeah. So.
Questions? No. Thanks.
Thank you.
And lunch you can find. This is campus and this is student center. Or go outside.